The history of superconductivity is a fascinating journey that dates back to the early 20th century. In 1911, Dutch physicist Heike Kamerlingh-Onnes made a groundbreaking discovery when he successfully liquefied helium and observed that the electrical resistance of mercury dropped to zero at temperatures close to absolute zero. This marked the first observation of superconductivity, a phenomenon that defied the conventional understanding of electrical conductivity. Kamerlingh-Onnes received the Nobel Prize in Physics in 1913 for this pioneering work. Following this discovery, researchers around the world delved into the study of superconductivity, leading to the development of various theories to explain this remarkable behavior of certain materials. In 1933, the Meissner-Ochsenfeld effect was observed, where a superconductor expels magnetic fields from its interior, providing further insights into the unique properties of superconductors. The quest for higher temperature superconductors gained momentum in the 1980s with the discovery of ceramic materials that exhibited superconducting properties at relatively higher temperatures. This breakthrough opened up new possibilities for practical applications of superconductivity in various fields. As of today, the highest temperature superconductor discovered operates at around -135 degrees Celsius, a significant advancement from the near absolute zero temperatures required in the early days of superconductivity research. This progress has paved the way for the development of superconducting technologies that can be utilized in real-world applications. The field of superconductivity continues to evolve, with ongoing research focused on understanding the underlying mechanisms of superconductors and discovering new materials with enhanced superconducting properties. The history of superconductivity serves as a testament to human curiosity and ingenuity in unraveling the mysteries of nature and harnessing them for technological advancements. Superconductivity is a phenomenon that continues to captivate scientists and engineers with its extraordinary properties and potential applications. At the heart of superconductivity lies the concept of zero electrical resistance, where current can flow through a material without any loss of energy. This unique behavior defies the laws of classical physics and opens up a realm of possibilities for technological innovation. One of the key characteristics of superconductors is their critical temperature, beyond which they transition from a normal conducting state to a superconducting state. This critical temperature varies among different materials, with some superconductors requiring extremely low temperatures close to absolute zero, while others can exhibit superconducting behavior at higher temperatures. For example, the first high-temperature superconductor discovered in 1986 had a critical temperature of around 30 Kelvin, significantly higher than previous superconductors. This breakthrough paved the way for the development of practical applications of superconductivity at more accessible temperatures. Another fundamental concept in superconductivity is the Meissner effect, where a superconductor expels magnetic fields from its interior, resulting in the phenomenon of perfect diamagnetism. This expulsion of magnetic flux allows superconductors to levitate above magnets, a visually striking demonstration of their unique properties. The type of superconductors can also be classified based on their response to magnetic fields. Type 1 superconductors exhibit a complete expulsion of magnetic fields, while Type 2 superconductors allow partial penetration of magnetic fields under certain conditions. This distinction is crucial for understanding the behavior of superconductors in different magnetic environments. The discovery of unconventional superconductors, such as iron-based and organic superconductors, has expanded the range of materials exhibiting superconducting properties. These unconventional superconductors challenge traditional theories of superconductivity and offer new avenues for research and technological applications. The field of superconductivity continues to push the boundaries of scientific knowledge, with ongoing efforts to discover room temperature superconductors that could revolutionize various industries. The quest for higher critical temperatures and more efficient superconducting materials drives research in materials science, condensed matter physics, and engineering. As we delve deeper into the basic concepts of superconductivity, we uncover a world of possibilities where electricity flows without resistance, magnetic levitation becomes a reality, and quantum effects govern the behavior of matter at the nanoscale. The journey of exploring superconductivity is a testament to human curiosity and perseverance in unraveling the mysteries of the universe and harnessing them for the betterment of society. Superconductors can be classified into different types based on their response to magnetic fields and critical temperatures. Type 1 superconductors, such as lead and mercury, exhibit a complete expulsion of magnetic fields when they transition to the superconducting state. These materials have a single critical magnetic field beyond which they lose their superconducting properties. In contrast, Type 2 superconductors, like niobium tin and yttrium barium copper oxide, YbCO, allow partial penetration of magnetic fields under certain conditions. This characteristic makes Type 2 superconductors more versatile for practical applications involving magnetic fields. The critical magnetic field of Type 2 superconductors is higher than that of Type 1 superconductors, enabling them to operate in stronger magnetic environments. Another classification of superconductors is based on their composition and structure. Conventional superconductors, such as aluminum and niobium, rely on electron-phonon interactions to achieve superconductivity. These materials typically have low critical temperatures and require cryogenic temperatures for their superconducting behavior. In contrast, unconventional superconductors, including iron-based and organic superconductors, exhibit superconducting properties at higher temperatures. For example, iron-based superconductors can have critical temperatures above 70 Kelvin, making them more practical for certain applications. High-temperature superconductors, such as cuprate and iron-based superconductors, have revolutionized the field of superconductivity by offering the possibility of operating at less extreme temperatures. The discovery of high-temperature superconductors has sparked intense research efforts to understand their underlying mechanisms and optimize their properties for various applications. The diversity of superconducting materials and their unique characteristics provide a rich landscape for exploring the physics of superconductivity and developing innovative technologies. Researchers continue to investigate new materials and novel superconducting phenomena to push the boundaries of superconductivity and unlock its full potential in areas such as energy transmission, medical imaging, and quantum computing. The superconducting phase transition is a critical phenomenon that occurs when a material undergoes a transformation from a normal conducting state to a superconducting state. This transition is characterized by the sudden onset of zero electrical resistance and the expulsion of magnetic fields from the interior of the material. One of the fascinating aspects of the superconducting phase transition is the critical temperature at which it occurs. For conventional superconductors, this critical temperature is typically very low, often below 10 Kelvin, requiring cryogenic temperatures for the material to exhibit superconducting behavior. In contrast, high-temperature superconductors have critical temperatures above 30 Kelvin, with some even surpassing 100 Kelvin, making them more practical for certain applications. The critical temperature is a key parameter that determines the feasibility of using a superconductor in real-world scenarios. Another interesting detail about the superconducting phase transition is the concept of coherence length. Coherence length is a measure of the spatial extent over which superconducting correlations persist in the material. It provides insights into the quantum nature of superconductivity and the interactions between electrons that enable the flow of current without resistance. The coherence length varies among different superconductors and plays a crucial role in determining their macroscopic properties. Understanding the superconducting phase transition and the factors that influence it is essential for designing superconducting materials with tailored properties for specific applications. Researchers continue to explore novel materials and mechanisms that can enhance the superconducting phase transition and push the boundaries of superconductivity to higher temperatures and improved performance. The Meissner effect is a fascinating phenomenon observed in superconductors, where they expel magnetic fields from their interior when transitioning to the superconducting state. This expulsion of magnetic flux results in the superconductor becoming a perfect diamagnet, levitating above magnets and demonstrating the remarkable properties of superconductivity. One interesting aspect of the Meissner effect is that it is a consequence of the formation of superconducting currents on the surface of the material, which create a screening effect against external magnetic fields. This screening effect is what causes the magnetic field lines to be expelled from the superconductor, leading to the levitation and repulsion of magnets. The Meissner effect was first observed in 1933 by Walther Meissner and Robert Oxenfeld, who noticed that a superconductor placed in a magnetic field would cause the field to be excluded from its interior. This groundbreaking discovery laid the foundation for our understanding of superconductivity and paved the way for the development of various superconducting technologies. In terms of numbers, the Meissner effect is characterized by the critical magnetic field, which represents the maximum magnetic field that a superconductor can withstand before transitioning to a normal conducting state. This critical magnetic field is a crucial parameter for determining the practical applications of superconductors, as it dictates the strength of magnetic fields that can be applied to the material while maintaining its superconducting properties. The Meissner effect is not only a fundamental aspect of superconductivity, but also a visually striking demonstration of the unique behavior of superconducting materials. Researchers continue to study the Meissner effect to uncover new insights into the physics of superconductivity and explore its potential for innovative applications in areas such as magnetic levitation, energy storage, and quantum computing. Magnetic resonance imaging, MRI, is one of the most widely used medical imaging techniques, providing detailed images of the internal structures of the human body without the use of ionizing radiation. MRI relies on the principles of superconductivity to generate strong magnetic fields and radiofrequency pulses to create detailed images of tissues and organs. One interesting fact about MRI is that the magnetic field strength of MRI scanners is measured in Tesla T, with higher field strengths leading to higher image resolution and faster scan times. For reference, most clinical MRI scanners operate at field strengths between 1 and 3 Tesla, while research scanners can reach field strengths of 7 Tesla or higher. The development of high-temperature superconductors has enabled the construction of more powerful MRI scanners with higher field strengths, allowing for improved image quality and diagnostic capabilities. Another fascinating aspect of MRI is its versatility in imaging different parts of the body, including the brain, spine, joints, and organs. MRI can provide detailed information about soft tissues, blood vessels, and abnormalities such as tumors, inflammation, and structural defects. The ability of MRI to visualize both anatomical structures and physiological processes makes it a valuable tool in diagnosing a wide range of medical conditions. In terms of numbers, it is estimated that over 36 million MRI scans are performed annually in the United States alone, highlighting the widespread use and importance of this imaging modality in healthcare. MRI is commonly used in various medical specialties, including neurology, orthopedics, cardiology, and oncology, for diagnosing conditions such as brain tumors, spinal injuries, heart disease, and cancer. The development of advanced MRI techniques such as functional MRI, fMRI, and diffusion tensor imaging, DTI, has expanded the capabilities of MRI beyond traditional anatomical imaging to study brain function, connectivity, and microstructural changes. These advanced techniques provide valuable insights into the brain's activity, white matter pathways, and neurodegenerative diseases. The continuous innovation in MRI technology, coupled with the advancements in superconducting materials, holds great promise for the future of medical imaging and personalized healthcare. MRI continues to evolve as a powerful diagnostic tool, offering non-invasive and detailed imaging capabilities for improving patient care and advancing medical research. Superconducting quantum interference devices, SQUIDs, are highly sensitive magnetic field detectors that leverage the unique properties of superconductors to measure extremely small magnetic fields. One interesting detail about SQUIDs is their ability to detect magnetic fields as low as a few femtotesla, which is equivalent to the magnetic field produced by a human brain or even a single neuron firing. This exceptional sensitivity makes squids invaluable in various scientific and medical applications, such as studying the magnetic fields of the brain, detecting magnetic anomalies in materials, and exploring fundamental physics phenomena. Squids operate based on the principle of quantum interference, where superconducting loops are interrupted by Josephson junctions that exhibit quantum mechanical behavior. These Josephson junctions allow squids to detect changes in magnetic flux with high precision, enabling them to capture subtle magnetic signals that would otherwise be undetectable. In terms of numbers, squids have revolutionized fields such as biomagnetism and geophysics, with over 1,000 squid-based systems installed worldwide for research and commercial applications. For example, in biomagnetism, squids are used to map the magnetic fields generated by the human body, providing insights into brain activity, cardiac function, and neurological disorders. The development of high-temperature superconductors has further enhanced the performance of squids, allowing for compact and more sensitive devices that can be used in a wide range of environments. The versatility and precision of squids have led to their adoption in diverse fields, including materials science, non-destructive testing, and mineral exploration. The continuous advancements in squid technology hold promise for future innovations in magnetic field sensing and imaging, with potential applications in quantum computing, astronomy, and environmental monitoring. High-speed maglev trains, short for magnetic levitation trains, are a marvel of modern transportation technology that operate without traditional wheels on tracks. Instead, these trains use powerful magnets to levitate above the guideway, eliminating friction and allowing for smooth and efficient travel at high speeds. One interesting fact about maglev trains is that they can reach speeds exceeding 600 kilometers per hour, making them one of the fastest modes of ground transportation in the world. The first commercial maglev train system, the Shanghai maglev, began operation in China in 2004 and has since been a popular choice for travelers due to its speed and comfort. Maglev trains offer numerous advantages over conventional rail systems, including reduced noise levels, lower maintenance costs, and higher energy efficiency. In terms of numbers, the Chuo Shinkansen maglev line in Japan is currently under construction and is expected to connect Tokyo and Nagoya with a top speed of 505 km per hour, significantly reducing travel time between the two cities. The maglev train technology continues to evolve, with research and development focused on increasing speeds, improving safety features, and expanding maglev networks globally. Germany, South Korea, and the United States are among the countries investing in maglev technology to revolutionize transportation and create sustainable urban mobility solutions. The potential for maglev trains to transform long-distance travel and alleviate congestion in urban areas has sparked interest and investment in this innovative mode of transportation. One of the current challenges in the field of superconductivity is the quest for room temperature superconductors, which would revolutionize various industries by eliminating the need for costly cryogenic cooling systems. Researchers are actively exploring novel materials and unconventional superconductors to achieve this breakthrough. Another challenge is the development of practical applications for high-temperature superconductors, such as power transmission cables and energy storage devices, to harness their full potential. In terms of numbers, the global superconducting materials market is projected to reach over $10 billion by 2025, driven by the increasing demand for superconducting technologies in healthcare, transportation, and energy sectors. Looking ahead, the future prospects of superconductivity are promising, with advancements in quantum computing, magnetic resonance imaging, and renewable energy technologies. The integration of superconductors into everyday devices and infrastructure holds the key to unlocking a more sustainable and efficient future. Superconductivity continues to captivate scientists with its remarkable properties and potential applications. The development of high-temperature superconductors has opened new possibilities for practical use, such as in high-speed maglev trains and advanced MRI systems. The global superconducting materials market is projected to exceed $10 billion by 2025, reflecting the growing demand for superconducting technologies. Researchers are actively pursuing room temperature superconductors to eliminate the need for cryogenic cooling and unlock new frontiers in quantum computing and energy storage. The Meissner effect, with its perfect diamagnetism and magnetic field expulsion, remains a fascinating demonstration of superconducting behavior. Squids, with their quantum interference and ultra-sensitive magnetic field detection, have revolutionized fields like biomagnetism and geophysics. Despite current challenges, the future of superconductivity looks promising, with ongoing research and innovation driving the field towards new breakthroughs and applications.